Hi chemists, in this last lesson of the unit, we're going to look at a different type of NMR spectroscopy that uses carbon as the nucleus for study. So we're looking at the carbon-13 isotope, and it's much simpler for the purposes of this class than what we saw with hydrogen NMR. The location of signals in a carbon NMR, just like it does for hydrogen NMR, tells us what kind of carbon is present. Saturated alkane carbons to the right, sp hybridized carbon atoms, followed by sp2 hybridized carbon atoms, and finally carbonyl carbon atoms, with a little range of electron poor carbon atoms attached to heteroatoms like halogens, oxygens, and nitrogens. That's all we're going to get out of this. We're not going to talk about integration or splitting for carbon NMR. It's primarily just used to determine the types of carbon atoms you have and how many different carbon atoms we have. So this whole lesson is around elucidating the structure of a compound given its molar mass from mass spectrometry. A hydrogen NMR is shown here that we've been talking about in the last few lessons. And what's new today is the carbon NMR. I'm actually going to start with that. If I look at carbon NMR, it's just the number of signals that tells us the number of carbons. Number of signals, for the most part, is the number of carbons. So if I look, I see all the way to the left, there's one. There's another one right there at around 130 and change. Notice I have some signals that are essentially twice the height of some of the others. That is likely indicative of the fact there are two carbons in the exact same environment by symmetry, right on top of each other. So the peak height actually is analogous to integration for what we saw in hydrogen NMR. There's two more little signals right there. There's another double height signal there, and then two more short signals off to the right. So if I add all those up, we've got 1 plus 2 plus 1 plus 1 plus 1 plus 2 more and 2 more. I've got 12 carbon atoms in my molecule. Oh, sorry, 10 carbon atoms in my molecule. So this is a C10 molecule. If we use the hydrogen NMR, we can look at the integration and just add those up as a first guess. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Also 12 hydrogens. So carbons and 12 hydrogens. Now that can't be the whole molecular formula because the whole thing weighs 164. Remember, we could get that from the very first thing we learned in this unit, based on mass spectrometry. Mass spectrometry does not give you a molecular formula. It gives you a molar mass, if you're lucky and the molecule stays as a molecular ion, which most of the time it can. So that there is something else present, C10 plus 12 H's plus something else, or perhaps many something else's, are going to equal 164 when we round to a whole number. Well, carbon is 12, and there's 10 of them. Hydrogen is 1, and there are 12 of those. So that gives us 120 plus 12, which is 132. And if I take 164 and subtract 132, we get 32. If you check your periodic table, that's pretty close to the molar mass of sulfur. So it could be 1 sulfur, or it could be 2 oxygens. And just as a good guess, we're more used to dealing with compounds that are oxygen containing than sulfur containing. So we'll consider both, but I'm going to guess that it has 2 oxygens in it, especially when I look at things like the rest of the data up above. This certainly looks like an OH peak right here, and this looks like an O-methyl, similar to some of the things we identified before. So now we'll look at the proton NMR, the hydrogen NMR, to try to figure out what the rest of the structure is. And there's many things that we've seen in the past. Flanking it all the way on the right seems to be an OH group. Remember, those can show up over a broad range of part per million shifts anywhere in the like 2s to 4s and beyond. But it's quite broad and a short little singlet that usually shows us the OH. We should take an IR. We'd be able to see in an IR spectrum if this had an OH or not, but they didn't give us that. But it's a good guess that it's there. This 3 hydrogen signal is most likely a CH3, but because of its location, I'm going to guess that it's an O CH3 because it's up close to 4. A 2 hydrogen peak here just suggests we have 2 hydrogens on some carbon. We don't know what else, although the splitting sure looks like a doublet. So there's probably an adjacent carbon with 1 hydrogen on it of some sort. And then we get to the left with much more electron-poor hydrogen atoms. This pair of doublets is the same as what we saw in the previous lesson. This is a para-substituted benzene, a para-di-substituted benzene. So there are 4 H's on a benzene ring where the substitution pattern on the benzene is a para-substitution. That just leaves these 2 signals, which are 2 distinctively different hydrogen atoms. And if I look at the location of the signals in the 6s, that's the vinylic range. 7s is aromatic, meaning off of something like a benzene, but the 6s are more vinylic. So this would be suggesting a carbon-carbon double bond, part of an alkene, potentially with 1 hydrogen on 1 carbon and another hydrogen on the other. And depending on what else is nearby, that would make sense in terms of the splitting pattern and the integration. So we can check the molecular formula. Do we have everything that adds up to the formula that we sort of proposed earlier, which we're going to guess, if we guess 2 oxygens, we're going to guess that it's C10 H12O2. They accounted for the carbons in the carbon NMR, and we have all the hydrogens, and we have the 2 oxygens as well. So now it's a question of how do we put these pieces of the puzzle together. Clearly the O-methyl and the OH are the terminal ends, one and the other, and then we have to figure out based on the splitting how the rest of these go together in some sequence. So hit pause and see if you can figure out what order these pieces go together to make our final molecule. Okay, so let's check and see how we did. This has to be an alcohol, and it is an alcohol that looks like this in the end. There's a couple of different guesses that you could have had. There's lots of ways, it turns out, that you can actually put these pieces together. And by trial and error, you might have discovered, mostly based on the splitting pattern, why we see this arrangement in the end. If we draw out all the hydrogen atoms now in this structure, we can identify where each and every signal comes from. The OH hydrogen, that's easy. That's that blip right there. Then we get to this CH2 group right next to the OH. These are quite electron poor because they're next to an OH. They're also allylic, so they feel both of those effects. So it's a little bit farther to the left than we would typically see OH hydrogens or hydrogens of an alcohol carbon. But it's not unreasonable that those explain that signal. They're split by the vinylic H right next to it. Notice alcohol H's do not split typically. I know that because there's no splitting in this OH. So if nothing causes a splitting of this signal, then this signal isn't splitting anything else. Splitting always goes in both directions. If you see me, I see you. That's how splitting works. So this 1 hydrogen right here would cause these 2 to be a doublet. What about this 1 hydrogen here? Well, he has those 2 right next to him, but he also has a 3rd on the alkene, and they're very different from each other. So instead of being 3 plus 1, a quartet, you actually get a doublet for that 1 hydrogen and a triplet for those 2. So you get what's called a doublet of triplets, which is often abbreviated DT. So if I highlight that hydrogen right there, that explains that vinylic hydrogen on that carbon. And then if we keep going and look at the other vinylic hydrogen, that would be that doublet right there. Makes sense if you look back at our structure. This hydrogen has 1 neighbor, and it's split into a doublet as a result. The benzene protons we've already sort of explained. There's our para-substituted benzene way out there, and that just leaves the CH3 group, which we've also sort of already explained, but that would be the O-methyl, and that falls in line with that signal. So we identified every signal based on all the information we used. This is an example of how challenging these problems can be, combining mass spectrometry, proton NMR, and now carbon NMR to elucidate a structure.